So, in the second part of talking about data science or data generally in healthcare, first thing I want to talk about is data quality. One of the issues that we run into all the time with healthcare data is missing data. Not everybody inputs every single thing that they're supposed to. Not everybody inputs stuff all the time. Like they're busy, they forget, it's not relevant. Different institutions have different requirements for what you can report, but then when you're pulling in information across the country, it's not always going to line up. And this happens sometimes. There's different types of missingness. There's like completely at random, missing, not at random. The crux of the issue here is, why is this data missing? So is it missing because there is a specific correlated reason for why the data is not entered? So for example, they don't enter heart rates for people who are coding because they're busy doing like CPR or something like that. Like they're not inputting a specific data point. It's as the problem if you use this data to train a model for prediction, because it's not going to see the actual reason why the missing data is missing and what effects that has downstream. So you need to think about that. We don't need to get into the nitty gritty. We only have a few minutes. But the issue that I'm sort of alluding to is it reduces the statistical power of whatever method you're using to draw insights from the data. So you need to think about when you do have missing data, why it's missing. And then the way that you address that is through imputation. Sometimes the fact that data is missing is itself a data point. But to impute, you can take the mean of everybody's blood pressure perhaps and just input that. You could take the median of everybody's blood pressure. You can come up with specific fun models to predict, based on everything else we know about this patient, we can sort of see what the model thinks this patient's blood pressure was. Or you could just not use blood pressure if you don't think it's relevant. Like half of your patients don't have a recorded blood pressure. And you have to consider these things. It is relevant to the model. If it is missing, how can I fix the missingness? Should I fix the missingness? Does the fact that the data is missing mean something clinically relevant? So things to consider, case by case basis. But a very, very big deal. Missingness is something we deal with a lot in healthcare data. Of course, bias inherent in the data. Just because we collect the data doesn't mean that it's necessarily correct or reflective of objective reality. Right? So then there's selection biases. Does the fact that a patient is prescribed insulin, is that related necessarily to our outcome? Well, there's indication bias for insulin. People who get prescribed insulin usually have diabetes, usually pretty severe diabetes, type 1 for sure, and then, type 2 diabetes unable to be controlled by other medications. So these patients are inherently going to be very, very different, like their medical history, compared to patients that aren't prescribed insulin. So comparing these two is sort of apples and oranges, and you need to account for that and there's various statistical methods that you can do to sort of counteract that, but then it's also just good study design, thinking about which two patient populations am I comparing? What are the differences between them? How can I make them as similar as I can for the purposes of, actually finding and weeding out the statistical differences between two groups that are essentially supposed to be the same, and making sure that they don't differ in important ways that you could otherwise be measuring. Confounding. And there's, measurement biases, like, does this machine is broken, it's going to measure this poorly, things like that. And then there's also biases in how things are recorded. It's, been mentioned before in various literature sources that clinicians will give diagnoses to people, different diagnoses to people, depending on things like their age, their race. Some of it, maybe is justified. Like, people who are relatively young usually don't get hit with an Alzheimer's diagnosis. And you're more likely to think Alzheimer's if you have an older patient, but there is some sort of a bias in there, and there's objective criteria for determining whether or not somebody has Alzheimer's. Age is part of it. But the point is, there are a lot of different factors that go into creating the data in the first place that can be affected by certain biases. There's also, biases in how you think about how to analyze the data. So the picture that's here is one of the classic pictures for something called survivorship bias. And if you haven't heard this before, go through it really, really quick. World War II, planes are coming back. This is a picture of like all of the bullet holes that they found on the plane. So then, one of the people says, oh, we should put a bunch of armor there because this is where all the planes that are getting shot are. So then we should put armor there. Actually, the answer turns out to be, you should put armor in the places where there are not bullet holes, because these planes made it back. The planes that got shot in the engine didn't make it back. So that's actually where you need to be focusing your attention, and not on the tips of the wings. These planes were able to make it home. This is called survivorship bias. Many, many different examples of bias like this. But again, this is all about data gathering. How do you interpret your data? How do you use your data? and thinking through all of these different fun logical fallacies and biases that might exist. So definitely something to be cognizant of to sort of help address data quality and make sure that when we say a patient has diabetes or a patient has heart failure, we're all talking about the same thing. There are healthcare data standards. So for terminology, there's SNOMED, LOINC codes, RX norm, RX norm for medications, LOINC for labs, some limited procedures. Then there's data exchange standards. How do you format your data? HL7 and FHR standards for how can you exchange data between two different EHR systems, two different hospital systems, so that when I receive it, I can just plug and play into my system, and then we have a data system that makes sense, and I don't have to spend, however many months trying to putz around with it to make sure that it works. And then coding for diagnoses. So like what you might be familiar with, ICD-10 codes, CPT codes for procedures. Diagnosis codes, how specific? I have diabetes with left chronic kidney function that's reduced with like right macular degeneration. You can get sometimes really, really specific with your diagnosis codes, but the point is that those serve a purpose. Are we all speaking the same language? When I say diabetes, do you understand diabetes the same way? As just a quick example, if you have a data sheet, you're thinking of your Excel spreadsheet, that if I type in diabetes with a lowercase and you type in diabetes with an uppercase, technically we know that they're supposed to mean the same thing, but you want to make sure that there's a standard. We should always write it this way so that when we collate the data, there's not like 4 different ways to spell diabetes. It's all just one, and we should all count them the same. So then how do we address this? Quality checks, like I've been mentioning before, a lot of this just comes down to good study design. You have to think about how to gather your data, think about your data, think about what it is you're trying to say, what you're trying to accomplish, and this dictates all of the things that we just mentioned before. You can do data profiling, exploratory data analysis once you've got your population together, once you've got your cohort, your data file, whatever. Take a look at it. How many of them are male? How many of them are female? How many of them have diabetes? How tall are they? What are all their BMIs? And you have to look, is it plausible? Look at am I trying to generalize this to the general population? Why do I have only 90% men? Why are 70% of them seem to have diabetes? That doesn't seem right. This is the case where if you're a clinician or if you're not, get a clinician who is specialized in this field or has experience doing these sorts of things. Look at the data together. Does this make sense to you? Are these two groups that we're comparing roughly similar? Are we gathering the right data to ensure that that is actually the case? These are the questions that you need to be asking yourself early and often. And then just sanity checks. Do these numbers make sense? And then data transformation. So once we get the data and we have to run it through models and stuff, I'll note that data needs to be in specific formats. So here's a test, fun example, sample of not real patients. But this is what the data might come to you as, and there's different types of ways that you can format the data. So then one is binary, presence or absence. So then that would be the rightmost column, diabetes, tested negative, tested positive. There's only 2 ways that it could be. Usually, like in statistics, you would code this as a 1 or a 0. And then there's continuous. Whether or not some things are actually continuous or not, it's a little bit of a pedantic debate among data science or informatics, but something like the plasma glucose concentration, it can be any number between 0 and a very, very large number. Sure, there should be a physiological top to that. And then you can, divide down into different decimals and stuff like that. So then that would be more continuous, discrete. Something like categorical. You could argue that age, if you do it by year, is discrete or categorical. But for example, we look at this column that says body mass index. I'm sure they're familiar. There are categories for body mass. Do we need the number? Does the number tell us anything? Does the number tell us more or less than the categories that we group them into? We can just say less than 18 or 18 and a half. We categorize that as anorexic or normal between 18 and a half and 25, yada, yada, yada. You can just have a column that instead of just giving the number for body mass index, something perhaps more clinically meaningful might be something like those categories, like we said before. And then this is where transformation comes in, because we can transform the data that we have, the body mass index, which as a continuous feature, and turn it into something categorical, if that is something that helps the model, that helps us describe our data to people when we publish it. Same thing with diastolic blood pressure or plasma glucose concentration. So sure, there might be categories, but what is the clinically meaningful thing it is that we're trying to accomplish or trying to say here? Is there a cutoff for what we can define as diabetes or not diabetes, or ketoacidosis or not ketoacidosis? And you can transform that continuous variable into something that's just binary. Yes or no. It's above or below the threshold. You need to make the decision that makes the most sense for your use case, given your understanding of the clinical meaning. And that's what I alluded to before. Transforming your data, you can have cutoffs, and then you can also have something like scaling. So this is an example of like houses and their age. And you can see here the number of rooms normalized here. Instead of, counting it between 0 and 100, there's like maybe one or two houses that have that many. But if you scale it so that 1 is actually just the maximum number that we have in our distribution, and 0 is the lowest number that we have in our distribution, this is more readable to you in a graph than the top one that's all condensed and flat, a little bit annoying to read. You can't really see the difference right now. But here you can see there's a little bit of nuance here, and then see if there's like a trend. There isn't here, but there could be, and only if you could see it scaled correctly. Now, scaling also has a contribution sometimes to model performance. Certain types of statistical models don't like huge, gigantic numbers. They get huge and gigantic really, really fast. I mean, if you can scale it between 0 and 1 or something like that, it plays better with the statistics. Sometimes this messes with your ability to interpret the data, because you want to be able to say like this sort of change in glucose by 50 milligrams per deciliter or what have you has this sort of effect on clinical outcomes. But in terms of like being able to visualize it, in terms of being able to model it, sometimes scaling it is something that you have to do. So for those of you familiar with things clinically, something like a D-dimer or something like a troponin. A normal troponin is very, very low. And then once you get a high troponin, it gets very, very high, very, very fast. Does a troponin of 100 versus a troponin of like 500 or 1,000, is that a clinically meaningful difference? You could try modeling it to find out. Does a D-dimer of 0 versus a D-dimer of like 100,000, is that clinically meaningful? Is 50,000 half as bad as 100,000 for D-dimer? Not necessarily. So then if you scale it, you could do like a log scale, you could do min-max like this. You actually might end up being able to get more clinically relevant stuff out of it. That's the end of this really, really quick crash course on data science, sort of data analytics in healthcare. If you have any questions, there's emails somewhere. Feel free to reach out.